Welcome to the webinar organized by Dynatest, talk about roughness evaluation. Just a small presentation of myself. I'm Umberto Pinori. I'm a senior PIM engineer at Dynatest, work for more than 15 years in payment survey and evaluation. I'm responsible for equipment and software application, some R&D activity, and lead of consulting unit. You have here my reference. You can contact me on socials. So if you have any point of interest regarding this webinar or other activity, please contact me. Some info about this webinar just before start. The webinar will be recorded. The camera is always off for all attenders. Attenders can sign as anonymous if they want. The attenders can switch on the subtitle themselves from option panel. For question, please use the chat space. And we try, but we are not sure if we are able to send the certification. An outlook presentation of the webinar. So we talk about roughness concept. Probably most of us are really well introduced in the roughness survey or activity or evaluation, but we start from a beginning point, and then we have a presentation of the equipment used for the profile measurement, and then we move on in the calculation of the roughness parameter. So we will have a presentation of which are the most used roughness parameter, or Rutting and macrotexture. And at the end, we present the Dynatest Explorer software, so how we elaborate in Dynatest our data. And there will be a space for question and answer. So first introduction, what is the roughness? So which is the idea that there is behind the roughness and what we want to measure associating to the roughness. So we need to define what is the roughness. Pavement roughness is generally defined as an expression of irregularities in the pavement survey that adversely affect the ride quality of a vehicle. So if you see here, there are a couple of roads picture below. Both of them, it seems that have irregularity, but the dimension of the irregularities in the left and right picture are different. And this dimension usually is called wavelength. And the wavelength of the left picture are shorter than the wavelengths in the right picture. Of course, these affect a lot the evaluation of the roughness. A roughness definition. This definition is provided by Ausroads. The road roughness is a condition used to measure deviations from the intended longitudinal profile of a road surface with characteristic dimensions that affect vehicle dynamics, ride quality, and dynamic pavement loading. So it's very important what is reported here in terms of characteristic dimension that affect. Because if you have a long bump, this bump will not affect the vehicle. So if you have small irregularities, the sum of these small irregularities along the pavement will generate higher rough values, and this will be reflected in discomfort for user and other problems. So it's important that we take into consideration which dimension we want to measure. Which are the roughness effects? So which is the contribution that a rough road introduce in the dynamic of the vehicle? Of course, the first one is that the vehicle is more complicated to control. So the driver has to put more attention or more effort in control the vehicle. The second one is the ride quality. Of course, the driver and the users and the passengers inside the road have a bad feeling of the road travel because they receive a lot of vibration or small bumps inside the car, and this is a discomfort for the passengers. Third point is a dynamic load. And this is important for the pavement because more the pavement is rough, more is the increasing of the dynamic load on the pavement. And this will be reflected in a faster damage of the road. So there will be a fast decreasing of the bearing capacity of the road, and this will be reflected in a higher maintenance cost. The fourth point is the drainage. Of course, if there is no perfect planarity of the road from the center to the right side, a correct slope, the water cannot we drive out from the road, and this will be reflected in accumulation of water on the road that can generate aquaplaning. The fifth point is the vehicle maintenance. Of course, vibration introduce a faster problem in the vehicle maintenance. And the last point is the fuel consumption. So a rough road required from a vehicle point of view a more consumption to move. Which is the dimension of the roughness? So what we are going to measure and why we are going to measure. So there are different levels of deviation from the through planar point of view. The first one is unevenness. So you have small deviation or small bump on the profile road. And this is usually is what affects a car. Then you have a slightly deviation of the through planar, and usually is between 50 millimeter and 0.5 meter wavelength. And this is usually something that affects the tire dynamic. Then there is a deviation that comes from the dimension of the grains that are on the surface course. And this deviation usually is influenced in the macrotexture. And macrotexture is between 50 millimeter to 0.5 millimeter. And then, of course, there is a deviation that is over the surface of a single grain. And this deviation over the surface of a single grain is called macrotexture. And macrotexture, of course, is below 0.5 meter. Macrotexture is responsible for the friction in dry condition. Macrotexture is influenced the friction in wet condition. But what is more important for the roughness for today webinar is the unevenness. And in our case, unevenness that affect the roughness is a deviation has wavelength higher than 0.5 meter, up to around 30 meter for the cars. So it's very important what we are going to measure. So an example of flat road. So these two pictures show roads that doesn't need that are characterized of a good rough level. So there is no bumps. But what is different in the left one, you see a completely flat land, and the second one, the road is a hill. But the dimension of this bump is so big that not influence the roughness. So the wavelength of this sag and bump are so big that from a roughness point of view, the road is still is like in flat condition. And now an example of rough road. In this case, you see two pictures where the pavement is more or less in a flat land area. In both of the pictures, there are small bump and small sag. So the deviation is small, and the wavelength is not so big, because if you see in this case, the wavelength is maybe 2 meter, 3 meter. In this case, maybe a little bit longer, but the wavelength dimension of this bump will affect a lot the roughness. So in this case, the quality of the road is not good because the roughness level is very high. How we can measure the roughness? Of course, a way to measure the dimension of this variation, you can use the rodent level or inclinometer. So these are typical topographic survey. Here is a reference of an ASTM standard that regulates the roughness measurements using this type of equipment. So the positive points using this type of equipment is that you have a reference profile. So you have the absolute height, the quote of single point. The biggest problem that the speed of the measurements is very low because it's below walking speed. The second type is the, of course, inertial profiler. In this case, the most common use standard is the ASTM E95 950, measuring the longitudinal profile of a traveled surface with an accelerometer, established inertial profiling reference. So we have an equipment that can be drive on the road and measure the roughness. So the different case from the previous equipment that the profile we get is relative. And what means relative? It's relative inside the dimension of the wavelength that the equipment can collect. And usually the maximum wavelength is around 100 meter for in road case. The positive point is that the measurements are really very fast. So here you can see a presentation of what we are doing. The equipment can be drive in the city or in the highway. It doesn't matter. It works from 0 to 100 kilometers. So it can be flexible in all conditions. And also there is a start and point, stop and go system. So also in the travel, the equipment can stop and can collect the profile. Which are the components that are inside the front bar you see in the video? We have a series of lasers that measure the elevation. Then we have 2D accelerometer that detect the vertical movement of the car, and they are used to compensate the vertical movements. Then we have a high precise distance measurement instrument. And then we have other additional equipment that can be raw camera in order to have picture of surrounding area, and GPS antenna. And of course here a picture of the electronics processing unit that collect all the information. So Dynatest produced two types of RSP equipment. The first one is called RSP Mark III. Is a front bar where we can install up to 21 lasers. As you can see here in this dark picture on the right, you see that all these red dots on the pavement, they are the laser pointer. So you see the big number of points we have along this bar. In this case, using a big number of points, we can measure also the cross profile. A Mark III can be installed only in front. And then we have a RSP Mark IV. The Mark IV is called a portable RSP, and it can be installed in front of the car or in rear position. Rear position also can be installed on towing vehicle, so it's very fast to remove and use on different cars. It can be equipped by 1 or 2 lasers, and the lateral position can be adjusted in order to fit in any vehicle exactly on the wheel track. So which is the reference for this type of equipment is the E950. And here you can see some requirements. It's very important that the sampling interval is maximum 25 millimeter, and the vertical resolution is 0.1 millimeter. So these are the two main characteristics that the inertial profile needs to have to be in class 1. Just to give you an idea of what the operator can see during the acquisition, this is the control panel. And so the operator can control the quality of the cross profile. Here you can see a movie of a real acquisition. In this window here, there is the vertical sensor signer. So you can see better here that this is recorded from all the two laser put in the wheel track and the one in the center. And then also the MPD, the mean profile depth for the macrotexture, can be shown on live. And all the other additional parameter, GPS, inertial motion system, and also IRI, so the roughness parameter is calculated live during the acquisition. So just to give you an idea of what is the longitudinal profile. This is an example of a longitudinal profile. You can see that in this case, you see 3 colors because it's the same profile collected on the left wheel path at the center and in the right wheel path. You can see that there is a 3/4 of this section that is characterized maybe from a small elevation, so the profile is quite flat. And then there is the last quarter where the profile has a huge variation in elevation. So of course, looking at the profile, you can expect that the first section of the road is still in low level of roughness compared to the last quarter, but just looking at the profile, you cannot make an evaluation. We need to calculate parameter in order to assign a judgment to the road. Here is a comparison in terms of profile of 2 different type of equipment. One is the inertial profiler and one is the inclinometer, so the 2 different standards. And as you can see, for the wavelength that influence the road, both profilers are more or less the same. Which are additional parameters that we can calculate with the RSP bar. Using a Mark III, you can install more laser, and more laser you use, and more and better you can describe the cross profile. And cross profile is very important to calculate the rutting. So, which are the parameters that can be used to evaluate the roughness? The most used one is the International Roughness Index, is the IRI. IRI simulates a car using a model with spring and bumper and some masses that simulate the car masses and the tire masses. Simulates the effect that the pavement generate on the car that travel at 80 km/h along the road. So, and here you can see in this video that more variation of the road there is, and higher is the IRI. So for any bump that the wheel receive, the IRI increase the value. So this is the concept of IRI. But across countries, you can see that a lot of other parameters are used to evaluate the roughness. So in some cases, very important also the straight edge, so the deviation from a straight edge, or the wave bands analysis. So any country probably has developed a different parameter. IRI anyway is the one that is internationally recognized. Here you can see some reference how to judge the IRI roughness. Here, this picture comes from the little book of profiling from Sayers. So you can see there are some interval to judge the pavement. So very important is these limits here is 1.82 for airport runways and new pavements in highway. And of course, more the pavement is less maintained or more aged, of course, the level of acceptance is increased. Here you can have some reference how Italian main company apply in the technical specification for the roughness judgment. And again, you can see that the limit is 1.8 for carriageway or for highway. Some isolated point can have IRI of 2x maximum. Of course, there is unacceptable thresholds that can be different case by case. So you can take this number as reference if you want. To give you an idea, also in the airport, we measure the roughness, but IRI is not recognized as a valid parameter because the IRI is properly developed for the cars. So the wavelength taking consideration for the IRI is the wavelength profile that affect the car movement. And the maximum wavelength is around 30 meters. But if we analyze the airport case, the dimension of the aircraft is totally different from the dimension of a car. And the distance between the nose gear and the landing gear is quite bigger compared to the car. So the distance between front and rear axle in a car is 2 meters, 3 meters. But in the aircraft case, the distance can be 15, 30 meters. So in order to consider this fact, the Federal Aviation Administration developed a new standard that take in consideration a parameter called Boeing bump index. The Boeing bump index take in consideration longer wavelength, up to 120 meters. And they developed this parameter specifically for the airport. So Dynatest is in the process to implement in Dynatest Explorer software also the BBI calculation. In order to simplify the elaboration phase, you can go on site, collect the information, and calculate the BBI parameter. The other parameter that can be calculated using the Mark III is the rutting. In general, the measuring rut depth of a pavement surface using a straight edge is described in the standard ASTM E1703. As you can see, you put a straight edge across the pavement and you measure the deviation. So the distance D between the road and the bottom part of the pavement deformation is the value of the rutting. Now, also another method is developed to measure also the water accumulation inside the rut. So, and this is the typical old method. Of course, this method is precise, but requires a lot of time to measure long distance because you have to move walking, you have to stop, go outside the car, place the straight edge, and then use the cone to measure the rutting depth. But using the RSP, you can drive up to 100 kilometers per hour and collect the information that are useful for the rutting evaluation every meter, every 10 meters. So this is the profile generated joining the single point collected by the RSP. And of course, you can create a virtual straight edge from the center of the lane to the external point, and the software can calculate the distance between the lowest point detected and the virtual straight edge. So the system is much, much faster. Another additional parameter that you can evaluate using the RSP is the macrotexture. The traditional method is the volumetric technique. So, or sand patch method allow to evaluate the macrotexture in terms of the estimated texture depth. And you can have here a standard reference. But of course, the laser can be used to measure also the different height between the grain peaks. Of course, the laser needs to be more precise, the one used just for roughness. So we need a vertical resolution of 0.05 millimeter and an horizontal resolution of 1 millimeter. So it means that a higher number of points needs to be collected, and this needs a higher frequency laser. Is important because there is in the standard is reported a correlation between the estimated texture depth and the mean profile depth. That is the parameter that can be used, can be measured or calculated from profiler. So using this equation, of course, can be compared the same value of macrotexture. And this is very important to correlate the old method to the new method. So now the presentation of the parameters is completed, and we are going to see the Dynatest Explorer software. That is the software that Dynatest developed to manage the profile collected during the acquisition. So this is the space. First point is, so now we are going to create a database. So multiple files can be imported inside Dynatest Explorer. So we are going to import. As you can see, many type of file can be imported in Dynatest Explorer. For what concern the profiling, the format that can be imported is .rsp, .erd, or .pro. So these are the three typical file format that are accepted from the software. So we select the RSP. We check just the import option. Soft, no process. Okay. So now a collected file is going to be imported. So you can see here is reported the name of the file. If you collect multiple lane, there is also you have more option as you want to save. If you want to generate one folder and single lane inside, or just all the lanes for both carriageway in the same folder. So there are different options for saving. So, and here you see most of the information that are collected during the acquisition. We have driving speed. So in this case, of course, was a city survey. You see that during the corner rounding, the speed is quite zero. But thanks to the stop and go system that Dynatest developed, the profile collected is still good for the roughness evaluation. We can have also event and bumps. So you can record some events, and more important, in this case, we have the raw camera. So for any station, we have the camera of surrounding area. So, and if we move one by one, we see that every 5 meters, a picture has been saved. So if you have problem or roughness, you can go here and see what there is of strange in the pavement. The graph can be adjusted. Of course, when you, in this case, we have 10 kilometers, that is a longer section, and maybe we can decide to split. So I can select 1 kilometer, or maybe also just 100 meter, and I can see the information I need in the easiest way. Then we have GPS data, but of course, this is just a plotting of the GPS data, but GPS will be associated in a second phase to the data. The most important one is IRI. So of course, here we have all the IRI plotted. If we zoom in, we see that we save IRI every meter during the acquisition. So in the RSP file, there is IRI calculated every meter, but is not very common. So usually we save we used to report every 100 meter. So you can go here. There is an option, averaging settings. So let's say that I want the interval is 100 meter, so 0.1 kilometer. I want to perform the averaging, and I say OK. So you can see that the graph now is changing, and this is more readable. There is also option to have only line and eliminate dots in case. We can decide which is the limit of any axis. So you see again that we have IRI value for left, center, and right. So left wheel track, center of the car, and the right wheel track. And again, we see that we have the last part that is characterized by higher value. All the graphical information, of course, can be seen also in table format. So we can go here and say view table, and I have the same data just seen in the graph in table format. So we have from the chainage, we have left, center, and right, and we have an average between left and right and the maximum value, because it depends on which type of evaluation you are performing. Sometimes it's more interested to see the maximum, or sometimes you want to see if the problem is in left, center, or right. And here you can see that we have the mean profile depth. So we have the MPD. This is the macrotexture of the pavement. In this case, the RSP was equipped with the texture laser. both in the left and right wheel track laser. So we have both. And again, here, data are saved every meter. And usually we plot at minimum of 10 meters. So we can see the variation. And as last one, we have the ride number that is a common parameter used to evaluate also the roughness, and we have the rutting value. So you can see here that the graph, there are some single spot point that detected a very high rutting value. And so also here you can zoom and you can see the amount of point we have. Here the rutting is reported every meter. We can perform an average of 10 meter. So we can better evaluate the trend of the rutting. And again, here we have 6 colors because we have left, full, right, left max, full max, and right max. So it means that for each interval this, selected for sampling, the software provides you the average value and the maximum value. And again, here we have a table format data. So all the software can be, all the data can be visualized in a proper way. Very interesting option is to have more data overlapped. For example, I want to see the IRI, the picture, and the rutting value. So, and you see that the software just put in one screen the selected option. And this is very interesting just to maybe, we know that in the last section, there is a more rough road. And the rough road is in combination also of rutting. So I can maybe decide to evaluate this piece here where we have a higher rutting value, and maybe we can see what there is on the pavement. And you can see that is a very rough road. And probably the rutting is because a missing part of road. So maybe here is a problem of potholes more than rutting. But this is important to show how much important is the raw camera to provide additional information to the engineer that is in the office and evaluate the survey results. So this part of the road is really bumpy also for this reason, because of course IRI is like 10, and IRI of 10 usually is something of unpaved road. So this was something strange, but was not important to just give you a judgment of the road, but provide you an example of how much the software is powerful and easy to move from one data to another data. Another very important option we have in Dynatest Explorer is the option to export in a map all this information. So if we go here, we can say view in DTMap. DTMap is the Dynatest map model created to show all the information. So we select this file. Okay, of course, in this case, we open just one file, but we can open also multiple files, and we select which is the parameter we want to plot. In this case, IRI. we can decide how many thresholds we want to judge the parameter. In our case, maybe we can use 2.5. We want in yellow 4.5. And over 4.5, we want to have red. You can decide, okay, IRI has only the value, but if you can use the max, the minimum, the division. And here you can also some evaluation, some option if you want to have line or points. When you decide, you say refresh map, fit zoom. And you can see that here you have the starting point and you see all the track that has been performed from the vehicle. And you see that the last part is where we have the rough road because it's in the hood for camping area. So this is very powerful because you can have a very fast visualization of where is the problem or where is the road that you surveyed. And then there is another important option. There is export map. So all this information can be exported in Google Earth. So we can say open. And all this information are plotted in Google Earth. And when you select each single piece, you have the information of the road. If you report in Dynatest Explorer the name of the road, the name of the lane, the data of collection, and the chainage, and of course the IRI value. So this is a very powerful tool to represent and report the results of the RSP investigation. And of course, the KML can be saved. And you can share the KMZ file with all your clients. So an easy way to share information that anyone can understand and immediately have a perception of the survey results. And again, here we can close. The last option I want to show you that all the information that we see in here in graph and in table format can be also exported to Excel. So we can decide to export to Excel, and in the export setup, you can decide if you want to average or not any single parameter that has been collected. So for example, I want to export only I want to export Rutting, mean profile depth, and IRI. So Rutting, mean profile depth, and IRI, and I want to perform. I want the Rutting every 10 meter, the mean profile depth every 10 meter, and the IRI every 100 meter. And an Excel file is generated. So you can see the Excel file is generated. So for the IRI, all the results are reported in left, center, and right value, and the average. And the value are averaged for 100 meter. We have MPD, where the result is reported in microns. Of course, as you can see, the center is 0 because there is no texture laser in the center. And this is for the Rutting value. So going to conclude a summary. In this webinar, we have seen what is a road profile and which is the characteristic of the road profile, the relationship between pavement profile and roughness. And because we need to know what we are going to measure to define the roughness. We see the equipment needed to collect the pavement profile, what is an inertial profiler, that is very important, which are the main parameters for roughness evaluation, and the use of Dynatest Explorer to elaborate data and report and create report and export results. And of course, how is important the geospatial representation of the data. So thanks for your attention, and please we leave 5 minutes for question and answer. So please write in the chat your question, and I'm pleasure to answer. One question is right number same as grip number for skid resistant value testing? No, no. The right number is a roughness parameter. So it is similar to IRI, but developed with a different algorithm. So grip tester is for friction or skid resistance, and right number is for roughness evaluation. So they are not the same parameter, are not referred to the same phenomenon. Just give me the time to read the question. Yeah. Yes, the equipment can. I will reply to Sam in a different moment because it's the longest to see. You say that the equipment can measure from 0 to 100. There is no lower limit. No, the equipment can be also used at 120 kilometer per hour. Dynatest developed a system to collect also at 0 kilometer. It's called start and stop and go. So the profile can be collected also when the vehicle reduce a lot the speed. Thank you for the presentation. Could you please present a brief on how I interpreted BBI? BBI is very important, is very easy to interpret. The acceptable limit is 1. So very soon Dynatest Explorer will be available to calculate the BBI, and the limit is always 1 as acceptable level. So when the BBI is over 1, there is a problem. Below 1, there is no problem. It's very easy to evaluate. Ideally, we operate between 30 and 100 km per hour standard speed at 80 km per hour. If we capture and measure at 5 meter interval with 3 camera, we try. Oh, yeah, it's good. So you have experience. Anyway, 80 km per hour is a reference, or 40 km per hour sometimes is a reference also for the algorithm in calculation. Of course, it's very hard to drive at constant speed. more constant is the speed and better is the survey. But of course, the algorithm in post-processing simulate a proper speed of calculation. For the BBI, but how correlate to the distance? No, the BBI, with the BBI for each single point, evaluate all the virtual or potential straight edge from 0 to 120 meter of straight edge and report for that point the highest value of deviation. So it's a longer process because for any point, there is a bigger number of straight edge that calculate the deviation. But one value for each single point is reported. Yeah, IRI on bridge point, on bridge joint or pavement joint. The joint affect a lot, IRI, and of course is a isolated point. There is a couple of international standards that provide a higher value of IRI as acceptable criteria. So it depends the technical specification you work on. Worldwide, people know that on bridge joint there could be problem. So, but we cannot remove the joints due to the construction of the bridge. So usually the acceptable criteria is different on the joint or along the road. So I hope to provide an answer to all the questions. There will be some other webinar in the future. We try to schedule one webinar every couple of months or something similar on different arguments. I hope to see you next time and have a good day. Bye.